so just before I start the actual tutorial today, I'd just like to say that an early access copy of my book, Hello Swift, has been released for the first 8 chapters. You can find it on many bookstores online, such as Amazon, Chapters, and Indigo, as well as the publisher's website. I really do hope that this helps you throughout your journey of learning the Swift programming language. Alright, so let's get into the tutorial now.
So hello there and welcome to another tutorial. My name is Tanmay Bakshi, and this time we're going to be going over how you can use the breadth first search algorithm in order to traverse a hierarchical graph or tree. Now let's actually begin today by saying, first of all, thank you to Nicholas, one of my subscribers, for actually sending in this question. In fact, you can see a picture of him on screen right now. Now, Nicholas actually originally came to me and emailed me with a question that said, how can you use the A-star algorithm in order to traverse an arbitrary graph or a hierarchical graph? And so I thought that, okay, this would be a great video idea. And so I started doing some research, but I realized eventually that it's actually slightly harder to let the A-star algorithm traverse a hierarchical graph than it is to have A-star traverse a maze. Something like this is harder to use A-star with than to do things like a maze. And in fact, you can see a link to a video where I tell you how to use the A-star algorithm with a maze in the description below. And the reason it's so hard is because you can't just directly say, okay, what's the distance between Toronto to Milton over here on this little graph? You'd have to calculate it using another algorithm. But we'll get into that later. But now you're probably wondering, well, what is this? Well, today I'm going to be using the question that Nicholas asked me, and I'm going to be answering it using this graph. Now, I've actually created this graph, and this graph essentially highlights a few of Ontario's cities. Very, very few of them. They're, I guess you could say, in the Greater Toronto area, and near Toronto in Canada. And so we have cities here like Markham, Vaughan, Brampton, Mississauga, Oakville, Burlington, Halton Hills, Aurora, and more. And so basically what we're going to be doing here is, as you can see, I've actually highlighted in kilometers the distance between any two cities that are connected by road. But there's one small problem. These distance values aren't distance values based off of roads. These are distance values from the latitude and longitude from the center of Toronto to the latitude and longitude of the center of Vaughan, for example. The reason I'm doing this is because I didn't want any complications where the roads go through other cities, and that's the length that we're taking. So in basically skipping all of that, these are the kilometer distance values between cities that are connected by road, but instead of getting the road distance, we get the air distance from the centers of those respective cities. That's basically what this graph consists of. In fact, since this is a little bit small to have on the whiteboard, and we're going to need a lot of whiteboard space to go through the algorithm, what I'm going to do is throughout this video, I'm going to have this actually popping up on the video screen so you can take a look at what I'm talking about. In fact, there's actually going to be a link to this graph in the description below. So what I'd recommend you do is you open up half of this on your screen and half of the actual video, so you can take a look at exactly what I'm saying in a bit more detail and stay in sync with what's actually on the graph. If you wouldn't like to do that though, don't worry, I will be showing the graph throughout the video in intervals. Alright, let's begin. Now, today, what my goal is to show you how you can use the breadth first search algorithm to traverse from Toronto to Aurora. Now, there's another question you might be wondering, and, well, why is the breadth first search algorithm named the breadth first search algorithm? Well, it's quite simple. The breadth first search algorithm will actually check a node's neighbors before checking those nodes' neighbors. Basically what's going to happen is it's going to check its own surroundings before checking the surroundings of its own surroundings, unlike how the A-star algorithm works. And so in some cases, I guess you could say the breadth first search algorithm is sometimes more efficient. In some cases, the A-star algorithm is more efficient. But that's a topic for an entirely different video. For now, though, video, I'm going to be showing you how exactly we can use the breadth first search algorithm in order to traverse a hierarchical graph. However, soon in the future, I will also create a video of how you can use the A-star algorithm to do this as well, and how you can use the breadth first search algorithm in order to traverse a maze. So I'm going to be creating a lot more pathfinding videos in the near future as well. Alright, but let's begin. So now, as you can see, on the graph screen right now, we've got two cities, Toronto and Aurora. And we've got a few cities in between these two cities, and we want to find the shortest way to get from Toronto to Aurora by going through some cities. And so the way we can do this is by, first of all, we note down Toronto. Okay, so we've got Toronto noted down. Now, where all does Toronto take us? Where all can we go directly from Toronto on this graph? So what we do is we draw an arrow and we say, okay, we can go from Toronto to Markham, Vaughan, Brampton, and Mississauga. Okay. But if you take a look at the graph on screen, you see that Mississauga is 22 kilometers away, Brampton is 32 kilometers away, Markham is 24, and Vaughan is 24 as well. And so Mississauga is the least distant from Toronto, then Markham and Vaughan, and then Brampton. So what I'm going to do is I'm going to list it in that order. Mississauga, Markham, Vaughan, Brampton. So, Mississauga, Markham, Vaughan, Brampton. Okay. Now, sometimes since like M repeats for Mississauga, Markham, Milton, and more, I'm just going to put an extra letter to signify Mississauga, Markham, ML for Milton, and more. Same thing for Brampton as well. Okay, so once we've got these down, then we're ready to move on to the next step. So we've actually noted down where Toronto can take us. And so what we're going to do now is I'm actually going to add a little superscript to each one of these, and I'm going to say T, meaning Toronto. And this means that this node was visited by Toronto. I'll tell you why this is helpful to us in just a moment, but here's a hint. We're going to be backtracking how we were actually able to get to our destination, and these superscripts will be extremely helpful. In a programming sense, what would happen is, let's say you've got MS as a node class, you'd have a came from variable or something of that sort, which is another node, and that's where you would store the superscript. That's how you would implement it, but this is how we're going to show it on the whiteboard. So, once you have drawn this out, then we're ready to move on to the next step, which is seeing, well, where can these four nodes take us then? So if I continue here, as you can see, what we're going to do here is let's take a look first of all at Mississauga. But one last thing we need to do before we move on to the next step is over our superscript for Toronto, let's make another superscript that notes down the distance between these two nodes. So Mississauga to Toronto is 22, then this is 24, oh sorry, not M, it's 24. So Markham to Toronto and Vaughan to Toronto are both 24, so I'm going to note down 24 and 24. And then for Brampton, we've got 32. Alright. So now that we've noted this all down, we're ready to move on to the next step. So our next step is going to be, and also just so you don't get confused, I'm going to draw a quick green line that'll signify this is one set, and now we're working on our second set of nodes. Okay. Alright, so let's begin. Now, Mississauga. Where can Mississauga take us to? So let's actually note down Mississauga on the side of our whiteboard over here. And we know that Mississauga can take us to, and you can see the graph on screen right now. It can take us to Oakville. It can take us to Milton. It can take us to Halton Hills. It can take us to Brampton, and it can also take us right back to Toronto. And also, by the way, in case you were wondering, you can see that there are some arrows between these nodes as well. Like, for example, there's an arrow between the connection that goes from Toronto to Mississauga, and that arrow points from Toronto to Mississauga. However, another thing I'd like you to note is that these arrows don't really mean anything. This is like bi-directional. You can go from Toronto to Mississauga using this route, and from Mississauga to Toronto using this route. These arrowheads mean practically nothing at this point. But continuing. So, now we know that Mississauga can take us to Oakville, Milton, Halton Hills, Brampton, and Toronto. Now, if you take a look in these two lists here, and not the list that we've already created, because it's blank anyway, if you take a look at these two lists, Toronto is already in one, so we remove it. Brampton is also already in the list. Milton is not, Oakville is not, and Halton Hills is not. So, we know that we cannot re-include Brampton and Toronto in our new list. So we, of course, erase those. But Halton Hills, Oakville, and Milton do seem like good candidates. So let's actually note down their distance values. So Oakville is 14 kilometers from Mississauga, Milton is 21, and Halton Hills would be 31. And these are actually perfect. And the reason these are absolutely perfect is because these are already in order. So 14, 21, 31. So all we need to do now is erase these, and then go back to our list over here and say Oakville, which comes from Mississauga. Alright, and since Oakville comes from Mississauga, we're going to note down its distance value. We're also going to say Milton here, which comes from Mississauga, and this is 21 kilometers from Mississauga. Then we've got Halton Hills, which is from Mississauga, and this is 31 kilometers away. Alright, so we've noted these down, and they are in order for Mississauga. Now let's take a look at how Markham handles this. So, let's begin. So Markham, as you can see, I'm going to note this down. And we've got Markham over here. Now, Markham can take us to Richmond Hill, it can take us to Vaughan, and it can take us back to Toronto. That's it. Now, Vaughan and Toronto are already part of this list, so we cannot include those. However, Richmond Hill has not yet been included in any of these lists. So what I'm going to do is I'm going to add a comma, and we're going to say in this new list, we're going to add Richmond Hill. That comes from Markham, and this is a 8-kilometer distance. And so that's how we note that down. Then we are done working with Markham, so we can remove this little area of our whiteboard. Then, finally, we can take a look at Vaughan. So, now Vaughan has quite a few different cities that it connects to. So, Vaughan does Markham, Toronto, Vaughan does Richmond Hill again, Vaughan does King, Vaughan does Caledon, and it does Brampton. Quite a few different cities. So now let's take a look at this. So Markham already exists in this set. Toronto already exists in the first set. Richmond Hill I'll talk about in a moment. King does not already exist. Caledon does not exist, but Brampton does. So we've narrowed it down to Richmond Hill, King, and Caledon. But then you take a look and say, hey, but wait, Richmond Hill already exists in the set. Well, we don't remove this Richmond Hill, we don't remove this new Richmond Hill just yet. What happened is, like, for example, Markham. Markham wasn't in this set, but it was in this set and this set. It was in a set before this one. And so what we do is we take a look at, okay, if Markham, or this node, was in the set before this one, then we cannot re-include it in the new set. However, Richmond Hill isn't in a set before this one. It is in this set. And so what we're going to do is we're going to take a look at both of these Richmond Hills. In the first Richmond Hill, we're going to take a look at how far away it actually is from Toronto. And the way we're going to do this is by using these superscripts I mentioned. So, if we take a look, over here, this Richmond Hill in the current set, ignore this one, currently, we go Richmond Hill to, where did Richmond Hill come from? Markham. So we go to Markham. Where did Markham come from? Markham came from Toronto. Okay, and what's the distance between Richmond Hill and Markham? That's 8 kilometers. And what's the distance between Markham and Toronto? As you can see, that is 24 kilometers. Then we just add 8 and 24, and then we get a good, that would be 32. All right. So we've got 8 plus 24, that's 32. So in total, from Richmond Hill to Toronto, using these superscripts, as you can see, that's a 32 kilometer distance. Now, if I were to take a look at this new Richmond Hill that's in the Vaughan set, let's take a look. So Richmond Hill in the new one goes to Vaughan, and then this Vaughan goes to Toronto, is our plan. Now, Vaughan to Toronto distance is 24 kilometers, and Richmond Hill to Vaughan distance is 7. And when we add 7 and 24, we get 31. And so as you can see, if we were to include the Richmond Hill from the Vaughan set, and not the Richmond Hill from the Markham set, then we would have a shorter path. We would have a shorter path, meaning a less number of kilometers to get back to Toronto from Richmond Hill. And so what we're going to do is, since we've decided that the Richmond Hill from the Vaughan set is shorter than the Richmond Hill from the Markham set, I'm actually going to erase this Richmond Hill. And in place, I am going to, of course, replace this with Richmond Hill from Vaughan, and this is a 7 kilometer distance. There we go. Then we can erase all of this extra work that we've done over here. Okay. All right. So we're done with that, but then we see we also have the King and Caledon over here. So we take a look at King. So King is how many kilometers away? It is 16 kilometers away. But Caledon is only 29 kilometers away. So of course we know that King comes after Caledon. King comes before Caledon in our final set. So we note down that we have King from Vaughan with a 16 kilometer distance, and we've also got Caledon from Vaughan, and this is a 29 kilometer distance. And then we are done with our Vaughan set, and we can erase this Vaughan information from here. But then finally in this set over here we've got Brampton, and Brampton is our last node. And so what I'm going to do is we're going to take Brampton here. Okay, where does Brampton take us to? Well, again, quite a few cities. So Brampton can take us to Caledon, Vaughan, Toronto. It can take us to Halton Hills, and it can take us to Mississauga. Now, of course, we can see that Vaughan, already in one of our older lists. Toronto is already in one of our older lists. Halton Hills, we'll talk about in a minute. Mississauga, already in our older list. Caledon, we will talk about in a minute as well. Now, let's start by talking a little bit about Caledon. So, as you can see over here, our older path with Caledon, what would happen here is we would go from Caledon to Vaughan, and this was a 29 kilometer distance, and then from Vaughan to Toronto, which was a 24 kilometer distance. And so the distance between from the older Caledon, already in our set, to Toronto would be 29 plus 24, and that would be 29, 24. So we would do 53 kilometers apart. And so what we should do now, though, is let's just take a look at our new Caledon. So our new Caledon over here. So our Caledon to Brampton distance would be 15 kilometers. Then our Brampton to Toronto distance would be, oh, sorry, I wrote Toronto in the wrong place. But our Brampton to Toronto distance would be, I can actually check that from the superscript that we've already written, and that's why it's so useful, 32 kilometers. 32 to Toronto. So now if we add those up, though, so 15, 32, we've got 47. So as you can see, the distance between Caledon to Toronto through Brampton is actually shorter than Caledon to Toronto through Vaughan. And so what I'm going to do is, as you know, we are going to take Caledon and we are going to erase it and do an in-place replacement, meaning it stays in the same I guess you would say element. It stays the same element in the array. It stays the same index, in the array. However, we just change its value. So Caledon comes from Brampton with a 15-kilometer distance. Alright, so once that's done, one more. We've got Halton Hills. Then we can also, of course, erase our work for Caledon. Alright. So now let's take a look at our older Halton Hills. So Halton Hills currently goes through Mississauga and then from Mississauga to Toronto. So if we were to write Halton Hills to Mississauga, which is a 31-kilometer distance, and from Mississauga to Toronto, and that is a 22-kilometer distance. If we were to add those up, so 31, 22, we've got 53 kilometers again. So Halton Hills is currently 53 kilometers away from Toronto through Mississauga. But if we were to, by chance, replace Halton Hills with Brampton, Mississauga with Brampton and go through Brampton for Halton Hills to get to Toronto, what would happen is, let's say our Halton Hills to Brampton distance is 23 kilometers. So our Halton Hill to Brampton distance would be, let's just make sure, that's 23 kilometers, as you can see on screen right now. Then Brampton to Toronto, as I noted before, would be 32. And so as you can see, if we were to add those up, 23 and 32, as you can see, that would be 55. But currently, we've got a 53 distance. So if we were to replace Mississauga with Brampton as the thoroughfare for Halton Hills to Toronto, we would be driving 2 more kilometers. And so we're not going to replace Halton Hills, and so we know it's not worth it to go through Brampton to get from Halton Hills to Toronto, or from Toronto to Halton Hills. And so we can, of course, erase our work for Brampton, because we know we're not replacing Halton Hills now, and we are done with the next step, but we still haven't reached our destination yet. We want to reach Aurora, which is another city. And so in order to get there, we've got to do a few more steps. So what we're going to do now is I'm going to once again create a little separator for you here between the next set and this current set. And then we can continue. So let's begin with Oakville now. Where can Oakville take us? Now, if we take a look at our map, though, if we were to draw out temporarily, Oakville takes us to, I'm just going to see here, so it takes us to Burlington, it takes us to Milton, and it takes us to Mississauga. Now, Milton, of course, this is our new set over here. This is our new set. This is our old set. This is an older set, and this is the oldest set. And so this one now, like for example, this Oakville can take us to Milton, but this is already in an older set. And so what we do is we say Milton won't work. Neither will Mississauga, because that's also in one of the older sets, and so Mississauga gets crossed out as well. So the only place that Oakville can take us to is Burlington. And so what we're going to do is we're going to note down Burlington in our set. So Burlington, which comes from Oakville, and our distance between would be 18 kilometers. And so once that's done, though, we can move on to Milton from our older set over here. Now, where can Milton take us? Let's see. So Milton can take us to, now again, quite a few cities. It can take us to the Halton Hills. It can take us to Oakville. It can take us to Burlington. It can take us to Mississauga. And so, basically, what we're going to say is, okay, Oakville, already there. Halton Hills, already there. Mississauga, already there. All we've got is Burlington. Now, though, Burlington is in our new set, our current set, I guess you could say. And so what we're going to do is we're going to calculate the total distance using these superscripts. And so Burlington currently goes through Oakville, and then Oakville, if we take a look at our superscript, goes to Mississauga, which goes to Toronto. Now, the Mississauga to Toronto distance is 22 kilometers, the Oakville to Mississauga distance is 14, and the Burlington to Oakville is 18. So if we were to add these all up, 18, I'm just going to draw this a little bit higher. So we've got our values 18, 14, and 22. Basically, as you can see, we've got a 54 kilometer distance here. So these are basically Burlington to Toronto or Toronto to Burlington using Oakville and Mississauga as thoroughfare. You're going to be driving, or flying in this case, for 54 kilometers. However, this is for our old Burlington. Let's just see, by chance, if we were to replace this Oakville with Milton, what would happen is Burlington would go to Milton, which would go to Mississauga, which would go to Toronto. Again, the Mississauga to Toronto distance stays the same, 22. I'll just draw that slightly clearer for you so you can see it's a 22. But since that value stays the same, we don't really care much about that value, so 22. Milton to Mississauga, however, will stay 21, and then Burlington to Milton will, of course, be 22. Now, you can obviously already tell that this is much higher. Let's just still add to make sure. So we've got 22, 21, and 22. So 22, 21, 21, and 22. Now, as you can see, basically, we're going to say 5 and 6, so 65 kilometers. So this is much, much more than what our current Burlington is, so we can successfully say that Burlington should not be replaced, Oakville should not be replaced with Milton in order to get from Burlington to Toronto, so Milton cannot offer anything for us to add to the set, and so we erase all of our work for Milton. There we go. All right, so we're almost half done, and now we take a look at Halton Hills. Where can Halton Hills take us? Well, let's draw that out. So Halton Hills can currently take us to, in total, Brampton, Caledon, Milton, and Mississauga. Okay, so now, if we take a look, Mississauga, again, is already gone, Milton is already gone, Caledon is already gone, and Brampton is already gone, so Halton Hills can take us nowhere. And so, Halton Hills is immediately deleted. Then we take a look at Richmond Hill, and you're probably getting excited now because it's very close to Aurora. Let's actually try this out. So, Richmond Hill actually takes us to Aurora, it takes us to Markham, it takes us to Vaughan, and it takes us to King. Now, even though we've reached our destination with this, our point is to not, of course, continue. Basically, we're not going to just stop here and say that, okay, we're done because Richmond Hill takes us to Aurora. That's not going to happen. So what we're going to do is, so Markham is already in our list, Vaughan is already in our list, then King and Aurora aren't. So what we're going to do is we're going to take a look at King. And so, first of all, King and Aurora. So Aurora from Richmond Hill is 14 kilometers, and King is 16 kilometers. So what I'm going to do is I'm going to add these in this order. So Aurora 14 and King 16. So Aurora comes from Richmond Hill with 14 of distance, and then King comes in from Richmond Hill with 16 kilometers of distance. Once that is done, though, finally we can continue. Now, the only reason that we're not just stopping at Aurora, though, is because, well, let's just say that, for example, King, we've already got King in our set, so King can also take us to Aurora. But let's just say that by chance, King is a shorter path to get to Aurora. We don't just want to stop at Richmond Hill, we want to continue and see and make sure that none of our other nodes can take us to Aurora in a much quicker way. But one more thing we have to take a look at is, as you can see, I added King to our set. But in our older set, we've already got King. So I'm going to remove this King here. Alright, so now we can continue. So, as you can see, we've got this set and we're done with Richmond Hill. Then we take a look at King from our older set. So King goes to, in total, again, quite a few cities. It goes to Newmarket, it goes to Caledon, it goes to Aurora, it goes to Richmond Hill, and of course it goes to Vaughan. Now, Richmond Hill's already in our older set, Vaughan's already in one of our older sets, Aurora, I'll talk about in a minute, Caledon's already there, and Newmarket isn't. So let's take a look at Aurora first. So our current Aurora goes through Richmond Hill, so it basically goes like this. Aurora to Richmond Hill to Vaughan, Richmond Hill to Vaughan, and then Vaughan finally goes to Toronto. Now the Vaughan to Toronto distance is 24 kilometers, Richmond Hill to Vaughan is 7, and then Aurora to Richmond Hill is 14. Okay, so if we add this all up, 14, 7, 24, as you can see, this basically becomes 5, 1 here, and that's 45. 45 kilometers currently, if we want to get from Aurora to Toronto through Richmond Hill and Vaughan. However, let's just say we were to replace the Richmond Hill with King. What would happen is we would be going from Aurora to King, and then from King, we would be going to Vaughan, and then from Vaughan, we would be going to Toronto. This is 24 kilometers. King to Vaughan would be 16 kilometers, and then Aurora to King would be 28 kilometers. So, if we were to add 28, 16, and 24, as you can quite obviously tell, it would be way, way higher. So this would be around 8, and then one more here, and so this would be 68 kilometers in total if we were to go through King and Vaughan instead of Richmond Hill and Vaughan. And that's why we are not going through King and Vaughan, and so we know that it's not worth it to replace this current Aurora path with the new Aurora path. So King can only take us to Newmarket, and that is with a 16 kilometer distance. So I'm going to just note that down. It can take us to Newmarket from King with 16 kilometer distance. And then, of course, we can erase our work for King, and we are almost done. Hooray! After so much work, just almost done. Then, finally, Caledon. So where can Caledon take us? Well, it can take us to quite a few places. So begin, Caledon takes us to, let's see. So it can take us to Brampton, Halton Hills. It can take us to King and Vaughan. Gonna make sure nothing else, and there we go. Alright, so it can take us to these 4 cities. Now, Brampton, already in our older set. Halton Hills, already, Caledon. Halton Hills, already in our older set. King, already in our older set, and Vaughan, already in our older set. So Caledon can take us nowhere, and we are done finding neighbor nodes for all of these nodes here. And so, we are done our 3rd step. Now, one thing you should notice here, though, is we don't need to go another step further, because we've already found our destination. We found Aurora in this set, and that is exactly where we want to go. And so all we need to do now is quite simply backtrace from Aurora to Richmond Hill, to Vaughan, to Toronto, and we have found our destination. So the way we need to go is we take a look at Aurora, and we write down, okay, Aurora. Where does Aurora come from? Well, Aurora came from Richmond Hill with a 14 kilometer distance. So it came from Richmond Hill, and the distance here was 14 kilometers. Then you take a look at the Richmond Hill from the other set, and Richmond Hill came from Vaughan with a 7-kilometer distance. So it came from Vaughan with a 7-kilometer distance. And then Vaughan came from Toronto, as you can see up there. And as you can see, the distance is 24 kilometers. And we have found our path to get from Toronto to Aurora and Aurora to Toronto. All we need to do now is calculate the distance. So 14, 7, 24. And finally, as you can see, if I quickly do the calculations here, we end up with a 45-kilometer distance. And there we go. We have completed our breadth first search testing here. And as you can see, what we've done is we've taken this hierarchical graph along with the distance values it represents, and we've been able to go from and traverse from Toronto to Aurora via Vaughan and Richmond Hill using the breadth first search algorithm. Alright, so that was it for this video today. Of course, I'd like to say a big thank you to Nicholas for actually sending in this question and giving me the suggestion for this video today. Of course, I will be creating many more videos about how you can use this with the maze and how you can use A star with this hierarchical graph. Alright, so that's going to be it for this tutorial. However, in the next part of this video, you're going to be seeing an actual implementation of this in Swift, along with my own implementation of how a hierarchical graph itself can be implemented in Swift. Alright, so that's going to be it for this video. Thank you very much for joining today. If you really liked the video though, and you want to show your support for it, please do consider leaving a like down below, as well as if you think if it could help any of your friends or family, do consider sharing the video as well. Of course, if you have any questions, suggestions, or feedback, you can leave them down in the comment section below, email them to me at taggymanny@gmail.com, or tweet them to me at taggymanny. Alright, so that's going to be it for this video, but one last thing before I go. If you'd like to be notified whenever I release new content, please do make sure to subscribe to the channel and turn on notifications to be emailed whenever I release new videos. Alright, that's going to be it for this tutorial. Thank you very much for watching today. Goodbye.